So in this video, we're going to discuss a very important topic that's called the instantaneous rate of change, or as many of you may have heard this referred to as the derivative. So first, let's start off by defining it. The instantaneous rate of change of a function at a point A is the limit of the average rate of change at A over smaller and smaller intervals. Perhaps the best thing that you want to get out of this is that this is called f prime of A. That is to say, this is the derivative at A. So just a couple things to be aware of. There's a few ways to define this. The derivative at a point x equals A is the same thing as saying the slope of the tangent line at A, which is the same thing as saying the instantaneous rate of change at A. And all of this is again referring to what we call f prime of A. That is the derivative at A. So let's look at this graphically and see what we mean by this idea of the instantaneous rate of change or the slope of a tangent line. So let's say we had some function. And the function takes on this shape. Where this is our input x and our output over here, we're getting our f of x value. Okay, so let's first talk about what this secant line thing is. And so let's say we want to explore this a value right here. And what's happening at that a value. The secant line is where we pick some other point and we connect them. And so the slope of that secant line, that is actually the same thing as the average rate of change that we were previously looking at. And what we want to do is keep moving secant lines closer and closer to that a value until eventually we are exactly at that a value. And this is what we mean by the tangent line. Notice that it's exactly only touching our function value at A. And so f prime of A would be the same thing as the slope of the tangent line. And so if I had to guess, I would guess f prime of A. Well, if you look at that, that's not a very steep line, right? But it definitely has a positive slope because it rises from left to right. So if I had to guess, I would guess f prime of A is positive, and I would guess it's not a very big number. I'm going to estimate that maybe it's about 1/2. Now let's look at a different example of a function. Let's say we're going to graph a different function. But now this function is actually doing something like this. And so let's say I picked A to be this point. And so we'd have a tangent line similar to something like this. So let's say this is our tangent line. What do you notice about the slope of this tangent line? Well, now this slope is some sort of negative number, and see how it's much steeper? I would guess that maybe this is about -3. And again, those two numbers, that 1/2 and that -3, those are just estimates looking at that tangent line and guessing what I think the slope might be. And so there's an important idea here. If you look at this graph on the left, f of x is increasing. Whenever the function is increasing, the derivative must be positive. So that's what this important note is here. If the function is increasing, the derivative is positive. if you look at my graph on the right, f of x is decreasing. If the function is decreasing, then f prime, the derivative, must be a negative number. So increasing functions have positive derivatives. Decreasing functions have negative derivatives. Alright, so we've looked at it from a graph, and now let's look at it from a table. So what we want to do is find the slope around very small intervals. Well, if we have a table, we don't have small intervals, but what we can do is some things to estimate what we think the derivative might be. So in this example, it says the total average farmland in the United States is given by the table below. Let f of t be the amount of farmland in millions of acres, and this is going to be a function of the year t. Okay, so looking at these values, do we think f prime of t will be positive or negative, and how do you know? Well, if I look at these values, as time goes on, these values are decreasing. If the function is decreasing, then we know the derivative must be negative. So I would say f prime of t is negative. And if somebody asks me how I know that because the function is decreasing. So let's say we wanted to find the derivative for 1995. This is the same thing as the slope, or the average rate of change at 1995 over the smallest interval that I can take. Well, the smallest interval looking to the left of 1995, I could do the slope with 1990. That's really the best that I can do to the left. So I would say f prime of 1995 is about, using the average rate of change formula, we look at our outputs, our change in our outputs over the change in the inputs. I would say that that's about 963 minus 987, right? The change in the outputs over the change in the inputs. 1995 minus 1990, those are my inputs. That gives us negative 24 over 5, which is negative 4.8. And really we should include units with this. Remember, our units are always our output per our input. So I would say that that is negative 4.8 millions of acres per year. So looking at approaching 1995 from the left, we think that we're losing about 4.8 million acres per year. That doesn't tell us exactly 1995, but gives us an idea leading up to it. So to get a better estimate, we want to look at what happens after it and consider that as well, so that we can get an idea of what's happening exactly at 1995. So if I was going to do a right-hand sum, I would really want to use the actual 1995 value and the value to the right. So I'm going to say f prime of 1995 is the change in the outputs, 945 minus 963, over the change in the inputs, 2000 minus 1995. And so that gives us negative 18 over 5, which is negative 3.6 millions of acres per year. Okay, and so what we're trying to do is actually estimate the exact rate of change in 1995. Well, this negative 4.8 million, that's the rate of change leading up to it. This negative 3.6 is after it. So I would estimate that it's somewhere in between those two. So I would take the average of them, negative 4.8 plus negative 3.6 over 2. And I would estimate that the actual derivative is negative 4.2 millions of acres per year. And that's really about the best that I could do. To be more accurate, I would need to know the years leading up to 1995, like maybe 1994, and the years after 95, like let's say 1996, to get a more accurate estimation of what the exact rate of change is at that moment. So let's now consider instantaneous velocity, which is a very similar idea, where what we looked at was, for average velocity, let's say, was the change in position over the change in time. To get instantaneous velocity, or the velocity at an exact moment, what we want to do is look at very short intervals around t and see what's happening at exactly, or as close to exactly, the moment of t as we can. And so just recall, we're looking at change in position over change in time. And what we want to do is use small time intervals. We want to shrink down time. So let's look at an example of how we can shrink time. Okay, so for example, in a time of t seconds, a particle moves a distance of s meters from its starting point, where s of t equals 4t squared plus 3. So this function right here, this is telling us position. And t is time. So what we want to do is look at very small intervals of time. Find the average velocity between t equals 1 and t equals 1 plus h for each of the following. So what we're doing is looking at change in position over change in time. So if h is 0.1, and we want to look at the change in these two things, okay, then our change in position over change in time would equal s of 1 plus h. Well, if h is 0.1, that's s of 1.1. Minus s of 1. Those are our positions, and our change in times would be 1.1 minus 1. And so if we plug all these values in, okay, we want to plug 1.1 into the original s of t function to get the position of the particle at the time 1.1. So that's 4 times 1.1 squared plus 3. And again, if you're not understanding where that number is coming from, that is this s of 1.1, or the position at time 1.1, minus 4 times 1 squared plus 3. So that value is actually corresponding to our s of 1. All that's our change in position now on the top, and we can go ahead and calculate this change in time. That'd be just 0.1. And if we work this math out, we'll get 7.84 minus 7 over 0.1. And really that just comes out to 8.4. So what does this number mean? That is the average velocity over this very short period of time, from 1.1 to 1 seconds. Or really, I should say from 1 to 1.1 seconds. So we're going to even shrink that time interval smaller. And we're going to do the position from s of 1.01 minus s of 1 over 1.01 minus 1. So again, we're looking at the position over an even shorter amount of time, how much the position changes. So if I did that, it'd be 4 times 1.01 squared plus 3 minus 4 times 1 squared plus 3 over 0.01. If you work that math out, you get 8.04. And so what that means is that over this shorter period of time even, that we've only added 0.01 seconds, during that time this particle did 8.04, and really if we want to think about units, and I could have put that there, that's meters per second. That's its average velocity during that really short time interval. So let's shrink that time interval even more. We're going to look at S of 1.001 minus S of 1 over 1.001 minus 1. So again, now we're just plugging in the position over an even shorter amount of time. That would be 4 times 1.001 squared plus 3 minus 4 times 1 squared plus 3 over 0.001. And if you work that out, you'll actually get 8.004. And so if you look, as you shrink the time intervals, you're getting closer to the actual velocity at exactly 1 second. So we could do that again even further with like 0.0001. But I don't think that's totally necessary, because hopefully you can see, what do these numbers appear to be approaching? I would say at the exact moment t equals 1, these speeds, these velocities appear to be approaching 8 meters per second. So I would guess that this particle at exactly the time t equals 1, at exactly 1 second, is going 8 meters per second.